Back. Hi, everybody. This is our final fifth installment to our kinetics unit. And today we're going to be talking about catalysts. And what is a catalyst? A catalyst is a substance that speeds up a chemical reaction. So it makes reactions happen faster. It does this by making a new mechanism, allowing a new pathway that the reaction can occur by that has a lower activation energy. Okay, and the catalyst in a reaction is always used up in one step, and then it's reproduced later on. So it sounds very similar, maybe, to an intermediate, and we'll talk about what is the subtle difference between those two when you're looking at a mechanism. Just to remind you, we're going to talk about a catalyzed version of the ozone decomposition reaction we talked about in the previous video. So here's the reaction energy profile. Remember, the activation energy was how much energy from the reactants here to the first or highest peak. Okay, in this case, it's transition state of the first step. Here's the mechanism and the overall process. And just a little bit more info. The first step we talked about takes quite a bit of energy for this ozone molecule to just break up and give off an oxygen atom. And so that actually happens in the stratosphere. That's where the ozone layer is, up high in Earth's atmosphere. So in the up above the troposphere, which is where we live, we breathe, and even where airplanes up as high as where airplanes fly. That's called the troposphere, and above that is this thin layer called the stratosphere, and that's where the ozone layer exists. And the ozone layer, it's photo-initiated. This depletion or this decomposition of ozone, that first step is photo-initiated. Okay, so it gets the activation energy that it needs from photons of light, and it actually absorbs in the ultraviolet region. And so the ozone layer actually protects us down here on Earth from UV light by absorbing it and breaking down in this way. And there's some natural processes that take oxygen and recreate the ozone up in the stratosphere as well. And so the ozone layer has stayed relatively constant for many, many years. And that actually got all changed by this man right here, Thomas Midgley Jr. This is going to seem a little unrelated, but I'm just going to give you some backstory on how he is related to the ozone layer. But prior to 1920, refrigerators and air conditioners used gases. So they pump gases and compress gases inside refrigerators and air conditioning units. And that's what actually provides the cooling effect that we utilize. And the gases that they used to use in those things were things like ammonia, sulfur dioxide, methyl chloride, and all of those had issues, okay? A lot of them are toxic. They're sometimes flammable, or they smell really bad. And so they were kind of problematic. If somebody had a leak in their refrigerator unit, or if they had a leak in their air conditioner, suddenly they'd either be getting poisoned, or there was a danger that the gas could catch on fire, or at the very least, it just smelt really bad and might make them feel nauseous. So they wanted to come up with some new gases that they could fill into those things that would have the same properties, but didn't have all these nasty, toxic and flammable and stinky properties as well. So Thomas Midgley Jr. was working for GM around that time, around the 1920s, and he developed these compounds called CFCs, and you've probably heard about them. They stand for chlorofluorocarbons. So CFCs are organic molecules that have carbon that's completely bound just to chlorines and fluorines. And they're actually really, really stable molecules. They are not toxic at all, and they have no smell. And they have excellent properties for what is needed in order to be used in a refrigerator or air conditioning unit. And so the first developed CFC looks like this. It's at one carbon bonded to two fluorines and two chlorines. Okay, so it kind of has the same shape as methane, right? CH4. But if you replace all of those hydrogens with fluorines and chlorines, as it's shown here. So that was actually called Freon, and you've probably heard about that as well. That's just the first CFC that was produced. Now, these CFCs actually ended up being pretty problematic for the ozone layer, and it wasn't necessarily well known at the time. But this guy Thomas Midgley, if you ever want to read more about him, he's a pretty awful person. Um, it's been said by environmental historian J.R. McNeil that he did more damage to the Earth's atmosphere than any other organism. Okay, so that's pretty awful. And I don't know if you've read any books by Bill Bryson, but Bill Bryson likes to write about science. He's a pretty engaging guy. His writing is pretty easy to read, and he's pretty funny as well. And he wrote in his book that Thomas Midgley Jr. had an instinct for the regrettable that was almost uncanny. So besides CFCs, he also produced or also came up with the idea to put lead into gasoline. And he's just had a whole bunch of, which ended up being very nasty. And I believe, if I remember correctly, he actually knew about some of these things. And so, not the best guy is the general message. But so anyways, going back to these CFCs, CFCs are very stable at our level, but once they get up to the stratosphere, they start getting exposed to UV light themselves. And so as we started using CFCs in refrigerators and AC units, sometimes they would leak, or even in the manufacturing process, they'd be released somewhat into the environment. And when they got up to the stratosphere, they were really stable, so they'd make their way up to the stratosphere, and when they were exposed to UV light, they would break apart. So oftentimes it would break one of these carbon-chlorine bonds to release a chlorine atom. And these chlorine atoms were what were really nasty for ozone. So chlorine atoms actually will catalyze the process of ozone decomposition. And we'll watch what happens here in these two steps. So if I have an ozone molecule and it encounters a chlorine atom, it will react similar in a kind of a similar way to the uncatalyzed process. But an ozone molecule will react with a chlorine atom to form an oxygen molecule and this ClO molecule. Okay, chlorine bonded to an oxygen. That thing is not very stable though. So if it encounters another ozone molecule, the ClO molecule will give off that oxygen back to the ozone molecule and produce two more oxygen molecules, and will reproduce this chlorine atom. So you can see that's the important part, is that the chlorine gets used up in this first step, but then it's reproduced in the second step. Okay. Now that makes it a catalyst, and that's why the chlorine atoms and all catalysts in general will never show up in the overall process, because they get used up but then produced, so they always occur on both sides of the reaction equation. I also have this ClO here, right? The ClO occurs on both sides, but that's actually different. That is a reaction intermediate. But you can see if that gets canceled out and the chlorine atom gets canceled out, we end up with the same overall process. Two ozone molecules decomposed to form three oxygen molecules. Okay, and here's what that catalyzed process would look like. Okay, again, we still have two steps here, so we have two humps, and you'll note that we have two transition states, one intermediate state, but we're at a lower activation energy. It takes less energy in order to do this, and so it happens faster. Okay, we're speeding up that process. Because catalysts are regenerated at the end of the reaction, we only actually need a tiny amount in order to catalyze a process. And actually, about 10,000 ozone molecules will get destroyed by just a single atom of chlorine in the stratosphere. And so these chlorine atoms were really harmful to the ozone layer. There was a marked decrease in the amount of ozone that was noticed in the late 1970s. So they had used these CFCs for many years before they realized it was really harmful. And one of the nice things is that it led to the Montreal Protocol in 1987. So this is sometimes pointed to as one of the most successful international environmental agreements ever. You've probably heard about people internationally, countries trying to reduce their carbon dioxide emissions, and that's been, have graded, at times it has greater or lesser effects. So This Montreal Protocol, though, was incredibly successful. So in 1987, a bunch of over 100, what is it, 197 countries signed the agreement. And since then, CFCs have been completely outlawed, and our ozone layer has actually mostly regenerated. So we actually had a problem. Everyone got together, agreed on a solution, and we made it happen. And our ozone layer is now regenerated. So it's something to look at as there's ways that we can do it, and sometimes these environmental solutions can be solved. These environmental problems can be solved. Enzymes. So let's look at some other catalysts. So we talked about chlorine atoms can act as a catalyst, but also in your body right now, there are enzymes that are catalysts. And you probably learned about enzymes in your bio class. An enzyme is a huge biomolecule. So, again, if we think about these proteins, it's really a protein. Proteins and things like that in organisms are enormous. So, this is an example of catalase, which is a particular enzyme. And you can see it has a molar mass of around 60,000 grams per mole. That's huge, right? You can imagine how many atoms are involved. And in fact, we can't even draw the Lewis structures. They try to make these things look a little clearer by drawing them with these different colors, different ribbons and whatnot to show how all these atoms are arranged in 3 dimensions. But they're really complicated structures. Now, catalase is actually an interesting one because it's present in almost, actually, I think all aerobic organism. So every aerobic organism, one that uses oxygen, okay, to fuel its body, they all have some form of catalase. And why is that? It's because when you have oxygen around, sometimes you'll form these things called peroxides, okay, and specifically hydrogen peroxide. And hydrogen peroxide, right, you pour it on your cuts when you want to disinfect it because it kills the bacteria, right, that might cause damage to you. So it's a pretty caustic chemical, and we don't want that forming in our body. And so catalase is an enzyme that catalyzes the process of decomposing hydrogen peroxide. And you can see what that process is like here below. So in the first step, a molecule of hydrogen peroxide, H2O2, reacts with the catalyst. In this case, it's catalase, but we're just going to abbreviate it by CAT, cat. And so the cat picks up one of the oxygen molecules and leaves behind a water molecule, right? That's not toxic. We're okay with that. And then in the second step, hydrogen peroxide reacts with the catalase with the oxygen on it, and it puts that oxygen onto one of the oxygens here. We end up with another molecule of H2O. We end up with an oxygen molecule, and catalase is regenerated unphased or unchanged. Okay? So we end up canceling out. Again, the catalase here is this catalyst, so that is canceled out because it is the catalyst. It occurs on the left and the right side. But we also have this. Again, the cat-O is produced and then used up. So if you remember, this is actually slightly different from a catalyst. It's an intermediate. So we would call that an intermediate. But again, it doesn't occur in the overall process because it occurs on the products and then the reactant side. And if you're like, well, how do I differentiate a catalyst versus an intermediate? The thing to look for is a catalyst is consumed, so it'll occur on the left side and then the right side, whereas an intermediate is produced, so it'll occur on the right side and then it's used up. So it'll be on the right-hand side of a step and then the left side of a step, and it's vice versa for the catalyst. So we cancel those out, and the overall process is 2H2O goes to water and O2. Catalysts can also, another way to analyze this and look at these catalysts is by calling them either homogeneous or heterogeneous. And this is thinking way back to the beginning of the course, but a homogeneous catalyst is one that's mixed in the same state as the substrate they're acting on. So the substrate is what is really the reactants in the reaction. So the catalyst acts on the substrate to make the reaction faster. So in the case of our chlorine atoms, the substrate was ozone. In the case of our the catalase enzyme, our substrate was hydrogen peroxide. Okay, and so if the catalyst is in the same substrate, or sorry, in the same state as the substrate, then we call that a homogeneous catalyst. So that would be like the enzymes, right? The enzymes, just like the hydrogen peroxide, are dissolved in your intracellular, liquids, fluids. So that would be a homogeneous substrate. A heterogeneous one is like your catalytic converter. So when your car combusts your fuel, it spits out all this nasty gas that has all these stuff, all these different partial combustion products. They're kind of nasty chemicals, but it gets passed over a catalytic converter, which is a solid. So the gas is passing through this solid, and the solid breaks down those things into just carbon dioxide and water. Okay, so the catalytic converter is there to make sure that all the stuff that comes out is just carbon dioxide and water and not other harmful things like carbon monoxide and other stuff. Okay, and it's nice to use heterogeneous catalysts in the real world because it's easy to separate them, right? If I have a solid and I just pass some gas through it, or I pass a liquid through it, it's very easy for me to just pick up that solid afterwards and separate it and reuse it again. But if I dissolve my catalyst into a liquid, well, then to purify it, to get the catalyst out, I have to somehow remove all the liquid and remove any leftover substrate, and it's hard to get your catalyst back. So usually it's better in industry, like when you're actually using these things, to use a heterogeneous catalyst. So here's an example of the types of problems you might encounter. Let's say you are given a reaction mechanism. So here's the reaction mechanism below, and it says it's catalyzed. Sorry, it doesn't give you that information. It just says you have a mechanism for the decomposition of nitramide, which is this molecule, and it wants you to answer some questions. So given is the mechanism, and it says what is the overall reaction equation for this process. Again, just like we did before, we're just going to add them all up. So we cancel out the hydroxide occurs on both sides. We also have this NHNO2 minus ion, right, that occurs on both sides. So when we cancel those out, we end up with nitramide decomposes to N2O and H2O. Identify any catalysts or intermediates that are present in the mechanism. Well, for a catalyst, we need to make sure it gets used up and then produced. So hydroxide is used up, and then in the second step it gets remade, so that would be our catalyst. And this NHNO2 minus ion gets produced and then used up, so that would be our intermediate. What would happen? So this is kind of going a little step further. What would happen to the rate of this reaction if some HCl were added? So HCl is hydrochloric acid. So we would think about, like, how would hydrochloric acid interact with any of these molecules or ions? And we aren't entirely sure how that's going to affect rate, right? But we could see how is it going to affect any of these. And we look at the catalyst, and the catalyst is a strong base, right? Hydroxide. So again, it's hard to necessarily predict exactly what's going to happen because we don't know if it's going to interact with these other molecules or ions, but we know that if it encounters some of that hydroxide ion, it's going to react with it. So we're going to lose some of our hydroxide ion, and because of that, we'll end up having a slower rate for this reaction. Okay, so that was kind of a complicated question, but it's something you could kind of maybe make a prediction of. And that's pretty much it. Okay, so catalysts, they're kind of cool, interesting things, but what you could actually get asked about them isn't too extensive. Just to recap what we talked about, catalysts make transformations, chemical transformations, happen faster by giving them a new mechanism with a lower activation energy. Again, the important step or important thing to focus on here is that it provides a new pathway with a lower activation energy. Sometimes students will say it actually lowers the activation energy, which is not correct. Okay, it's not just lowering the activation energy for a reaction; it's providing a new pathway. So the way I kind of think about it is, if I'm trying to go over a mountain, let's say, the uncatalyzed process would be like just walking up and over the mountain, whereas the catalyzed process would be digging a hole through that mountain and just passing through that hole. Okay, so it's a new pathway that happens to have a lower barrier of energy. Okay. Catalysts are used up and then reproduced later on in a mechanism, so you can identify them in a mechanism that way. Enzymes are huge biological catalysts, and they're actually very specific to certain reactions. So catalase, for example, that we looked at, is only effective at catalyzing the decomposition of hydrogen peroxide. So it's very specific stuff. It doesn't work in all these other molecules, right? And that's really important. That's why we have these enormous enzymes. That's why they're so big, is because all of those atoms are used to fine tune it so it only works for one specific reaction. Okay? If it catalyzed the decomposition of lots of different molecules, it might be very problematic to have that inside you. Lastly, catalysts can be homogeneous or heterogeneous. Heterogeneous catalysts we talked about are more easily separated and reused. So in the actual world, that's what you want to use. But actually, it's easier to study something that's homogeneous in a solution. So when we're actually developing catalysts, a lot of times we look at homogeneous ones to understand how they react, and then somehow we can sometimes get those to be heterogeneous. But that's a problem, a dissonance there, where the heterogeneous catalyst is more useful to us, but it's more easy to analyze and develop homogeneous ones. So, anyways, that's a lot of maybe tangent information, but hopefully you found it interesting. And that's it for kinetics. So I hope you enjoyed some of these videos, and we'll see you tomorrow. All right, bye.